Right now, the quantum world is rewriting everything we thought we knew. The smallest components of nature do not follow the steady, predictable rules of classical physics. They shift, fluctuate, and respond to observation in ways that reshape our entire picture of reality. In this documentary, we will trace how that discovery unfolded, from the first clues hidden in atomic spectra, to the experiments that revealed wave-particle duality, to the breakthroughs that allowed us to measure time with electrons and detect gravitational waves with quantum light. Each idea arrives quietly, built from real data, real instruments, and real history, opening a path through the quantum structure of the universe. And from here we step into the first question. Part 1. Why did quantum physics replace the predictable universe we thought we understood? When the 20th century began, physics felt complete. Students were told that the laws of nature were steady, clean, and entirely predictable. A falling apple followed a calculable trajectory. A planet traced an elliptical orbit that could be forecast centuries ahead. Engineers used Newton's equations to build bridges, ships, and engines with confidence bordering on certainty. For a while, it seemed that if one only measured precisely enough, every future event could be computed in advance. But beneath that calm structure, something was already cracking. Small anomalies had begun to appear. Tiny mismatches between theory and measurement, almost invisible at first. When scientists studied the glow of heated metals in the late 1800s, the spectrum of colors did not match classical predictions. The ultraviolet catastrophe predicted infinite energy at high frequencies, an absurd outcome no experiment supported. Max Planck, trying only to fix the mathematics, proposed that energy could be emitted in discrete amounts. He later called this step an act of desperation. Those discrete amounts were the first hint that nature behaved in increments, not in smooth continuums. And though Planck did not yet know it, this adjustment opened the door to a new world. A world that would soon replace determinism with probability. Another crack appeared when scientists explored the structure of the atom. Classical physics treated electrons like tiny planets orbiting a miniature sundae. But if that were true, each electron would radiate energy continuously, spiral inward, and collapse into the nucleus in a fraction of a second. Atoms clearly existed, so the model could not be correct. Niels Bohr attempted a fix in 1913 by proposing quantized orbits, allowing electrons to occupy only certain discrete energy levels. His formula matched experimental spectra with remarkable accuracy, but the idea itself lacked a classical explanation. As experiments advanced, the cracks widened. In 1905, Albert Einstein published a paper showing that the photoelectric effect, light ejecting electrons from metal, could only be explained if light behaved as packets of energy, later called photons. This was unsettling. All scientific experience until then described light as a wave. Now, under certain conditions, it behaved like particles. The dual behavior was real, measurable, and repeatable, but it defied every classical picture. Physicists realized that the deeper they looked, the less stable their old rules became. A crucial moment came in the 1920s, with experiments such as the double-slit test. When a beam of electrons passed through two narrow slits, it produced an interference pattern, something only waves should create. But when detectors were added to check which slit each electron used, the pattern vanished. Electrons behaved like particles whenever someone looked, but like waves whenever no measurement was made. The experiment has been repeated countless times, with electrons, protons, atoms, even molecules containing more than 100 atoms. The result is always the same. Some physicists tried to repair classical determinism. They searched for hidden variables that might restore predictability, but every attempt to create a classical explanation failed. Richard Feynman explained the situation directly to his students. Nature isn't classical, and if you want to understand it, you better learn quantum mechanics. What replaced determinism was not chaos, but probability. A particle's location became a distribution of possibilities. Its motion was not a line on a graph, but a cloud of outcomes, each weighted by likelihood. The mathematics describing these probabilities, wave functions governed by the Schrödinger equation, produced results that matched experiments with unmatched precision. Quantum mechanics became the most accurate scientific framework ever created, but accuracy did not eliminate strangeness. Consider a simple example: an electron bound inside a hydrogen atom. Classically, one might imagine it orbiting like a small planet, but measurements show no orbit at all. Instead, the electron exists as a standing probability wave around the nucleus, a distribution that fills space quietly and continuously. When measured, it appears at a single point. When not measured, it behaves like a spread-out wave. The transition between these two descriptions, smooth wave to point-like detection, is not something classical physics can explain. Or consider radioactive decay. A nucleus does not break apart because of an internal clock. Instead, quantum tunneling allows a particle to escape by crossing an energy barrier it classically should not overcome. The exact moment of decay cannot be predicted, only the probability per unit time. This probabilistic nature is why radioactive dating produces half-lives, not guaranteed lifetimes. Another example comes from superconductivity. Below a certain temperature, electrons in materials like niobium or lead pair into Cooper pairs and move without resistance. The mechanism requires quantum mechanics to describe how electrons, which normally repel each other, behave collectively as a single quantum state. Classical electrodynamics cannot produce such a phenomenon. Quantum behavior also governs the semiconductors inside every phone and computer. The reason a transistor works, its ability to switch and amplify signals, depends entirely on quantum energy bands inside silicon or gallium arsenide. Without quantized energy levels, electronics as we know them would not exist. Each example points to the same conclusion. Nature at its smallest scales obeys rules that have no classical counterpart. The shift from determinism to quantum mechanics was not philosophical, it was empirical. At every step, experimental data pushed physicists toward new explanations. They did not abandon classical physics because they wanted novelty. They abandoned it because the numbers demanded it. Historical moments illustrate this transition clearly. At the 1927 Solvay Conference, figures like Einstein, Bohr, Schrödinger, Heisenberg, and Dirac gathered to confront the meaning of quantum observations. Photographs from that meeting, still published in physics textbooks, capture a turning point in scientific history. Einstein challenged the probabilistic nature of the theory, insisting, God does not play dice with the universe. Bohr responded that it was not for humans to dictate how nature must behave. Experiments consistently supported Bohr's view. By mid-century, quantum mechanics expanded further. Quantum electrodynamics, QED, developed by Feynman, Schwinger, and Tomonaga, predicted the electron's magnetic moment to astonishing accuracy. Measurements matched theory to more than 10 decimal places. Few scientific models have ever achieved such precision. Gradually, the scientific community accepted that determinism was an approximation, useful for large objects, but not fundamental. At small scales, probability ruled. Measurements did not reveal an underlying certainty, they created the outcome itself. Observation became part of the process, not a passive inquiry. This did not imply consciousness altering reality, but rather that the act of measurement involved interactions that forced a quantum system into a definite state. Quantum mechanics reshaped every field it touched. Chemistry became a quantum science. Materials science became a study of quantum energy bands. Astronomy embraced quantum processes in stars, white dwarfs, and neutron stars. Nuclear physics emerged from quantum interactions inside atomic nuclei. Even today, quantum mechanics continues to expand. Technologies such as atomic clocks rely on quantum transitions in cesium or strontium atoms. Laser systems depend on stimulated emission, a phenomenon predicted by quantum theory. Quantum sensors detect faint gravitational waves and subtle variations in magnetic fields everywhere we look. Inside atoms, across laboratories, and even in large-scale instruments. Quantum rules shape the observable world. As the 20th century unfolded, The tidy, clockwork universe dissolved. What replaced it was not disorder but a different kind of order. An order built on statistical behavior, measurable probabilities, and physical laws that describe how reality behaves when viewed at the smallest possible scales. Quantum mechanics did not destroy classical physics. It completed it, extending the framework into domains where classical laws no longer apply. This is why the first part of the documentary begins here, with the moment the scientific world realized that the foundations of nature were not predictable paths, but probability waves. The shift did not happen overnight. It emerged through decades of experiments that contradicted the simplest expectations. Yet each contradiction pointed toward the same truth. Nature operates according to quantum rules, even when classical approximations appear to work. Some concepts remain challenging, but the underlying motivation is simple. Experiments forced a new understanding. Measurements contradicted classical intuition. Patterns emerged only when quantum principles were applied. Precision instruments revealed behaviors that classical equations could not reconcile. Bit by bit, the evidence accumulated until the old framework could no longer hold. From those measurements, physics slowly learned how differently nature behaves at very small scales. And that understanding did not remain confined to laboratories or equations. It began to shape how scientists interpret signals arriving from far beyond Earth, where gravity becomes intense and matter is pushed to its limits. That shift becomes impossible to ignore in the next part. When attention turns to a single X-ray signal recorded in 1971, a signal from Cygnus that forced researchers to reconsider whether black holes were mathematical ideas or physical objects, leaving measurable traces in the sky. Part 2. Why did a single X-ray signal from Cygnus in 1971 force scientists to admit black holes are real? The moment Cygnus X1 lit up NASA's detectors, something in astrophysics cracked open. For decades, black holes had hovered on the edge of theory. Possible on paper, questionable in nature, and doubted even by Einstein himself. But in 1971, a burst of high-energy X-rays arrived from a point in the constellation Cygnus with a violence no ordinary star could create. It was the first sign that the universe was hiding something far denser, far darker, and far more compact than anything classical physics could explain. When NASA launched the Uhuru satellite in December 1970, its goal was simple: survey the sky for X-rays with more precision than any previous instrument. The detectors were not sophisticated by today's standards. Proportional counters mounted on a spinning spacecraft. But they were stable, sensitive, and designed to map sources across the sky with steady accumulation. Only a few months after launch, astronomers analyzing the data found an object radiating intensely in the high-energy band, flickering in rapid intervals that implied extreme gravitational forces. They labeled it Cygnus X1, the first bright X-ray source in Cygnus. To understand why this signal mattered, we need to recall what X-rays reveal. Ordinary stars emit most of their energy in visible light. Even hot blue stars or white dwarfs rarely produce strong X-ray emissions. X-rays emerge from matter, heated to tens of millions of degrees. Temperatures reached only when gas is compressed violently by enormous gravity. The most common environment for such heat is an accretion disk around a dense compact object. For Cygnus X1 to shine with this much intensity, something had to be pulling matter inward at extreme speeds, heating it to temperatures far beyond anything in a normal star's interior. The early analysis revealed something just as important. The source showed rapid variability. The brightness could change over timescales shorter than a second. In astrophysics, a changing timescale tells you about size. If an object brightens or dims in 1 second, it cannot be larger than the distance light travels in 1 second. Roughly 300,000 kilometers. That constraint alone implied a region smaller than Earth's diameter, nothing but a compact object. A neutron star, or black hole, could fit those limits while generating that much energy. But there was more. Astronomers soon discovered that Cygnus X1 was part of a binary system. The visible component was a blue supergiant star named HDE 226868, several tens of times more massive than the Sun. The star's motion revealed it was orbiting an unseen companion, and using Doppler measurements, scientists could calculate that the invisible object had a mass greater than about 15 suns. No neutron star can reach such mass. Even at their densest state, neutron stars collapse under their own gravity if they exceed roughly 3 solar masses. That limit forced the conclusion that the unseen object in Cygnus X1 was too heavy to be anything but a black hole. For the astronomy community, that realization was not gentle. Black holes had been theoretical constructions for decades, permitted by Einstein's general relativity, yet doubted as physical realities. Einstein himself wrote in 1939 that nature would resist forming them. Many physicists believed that collapse would halt before reaching the densities required for a true event horizon. Cygnus X1 contradicted those expectations directly. Kip Thorne later summarized the moment clearly. Cygnus X1 was the moment we crossed the line from speculation to certainty. Thorne's statement captured something deeper. Black holes were no longer mathematical conveniences. They were objects that could pull matter, deform space, and heat in falling gas into a furnace of X-rays detectable across thousands of light-years. But to move from suspicion to confidence, scientists needed more than orbital calculations. They studied every wavelength. In radio frequencies, Cygnus X1 emitted jets, characteristic of matter being funneled through intense magnetic fields near an accretion disk. In visible light, small fluctuations in the companion star's brightness indicated tidal interactions caused by a compact partner. In X-ray spectra, the signature of high-energy photons matched the temperatures expected when gas spirals inward toward a gravitational abyss. Each detail fit a single interpretation: a stellar mass black hole feeding on its companion star. Behind these observations were long nights of careful measurement. Engineers monitoring Uhuru's detectors made constant calibrations to reduce noise. Astronomers cross-checked the data using ground-based telescopes in Chile, Arizona, and South Africa. Each dataset reinforced the same picture: a massive, invisible object, compact beyond classical limits, drawing matter into a disk that heated to millions of degrees. The discovery arrived at a turning point in astrophysics. Before Cygnus X1, only theoretical arguments pointed to the existence of black holes. After Cygnus X1, observational astronomy itself began to adapt to a new reality. X-ray astronomy expanded rapidly. NASA launched satellites like HEAO-1, ROSAT, and later Chandra, each with finer resolution. ESA added XMM Newton, offering deep spectral analysis. With each mission, more compact objects appeared. Many were neutron stars, but a significant number exceeded the mass limit, revealing themselves as black holes. Cygnus X1 was the first crack in the wall. Many more followed. This changed not only our understanding of stars but also our view of galaxies. Once scientists accepted stellar mass black holes, they began re-examining the centers of galaxies. For decades, some had suspected that galaxies contained compact, massive objects, but the idea lacked firm grounding. Now, with Cygnus X1 providing proof of concept, astronomers looked deeper. By the late 20th century, instruments such as the Very Large Telescope and the Keck Observatory measured the motion of stars near the center of the Milky Way. The velocities were extreme. Some stars moved at more than 5,000 kilometers per second. Only a very massive object in a very small region could cause those motions. In 2020, the Nobel Prize in Physics recognized this discovery, confirming a supermassive black hole about 4 million times the mass of the Sun at the Milky Way's core. This, too, can be traced back to the confidence built from Cygnus X1. The first detection created the framework that allowed scientists to identify black holes on vastly larger scales. Other galaxies showed similar signatures. NASA's Chandra Observatory identified X-ray flares from the center of M87. ESA's Gaia tracked stellar orbits in nearby galaxies. Eventually, the Event Horizon Telescope provided the first image of a black hole's shadow in 2019. These later breakthroughs were built upon decades of techniques developed because Cygnus X1 forced astronomy to accept black holes as physical objects. The journey from a single X-ray signal to the first direct image of a black hole was long, but the connection is direct. Without Cygnus X1, the observational methods that made the EHT possible may not have developed as they did. To appreciate the scientific weight of the discovery, it helps to understand the environment around Cygnus X1. Matter stripped from the blue supergiant spirals inward, forming a disk where friction and magnetic turbulence heat the gas to tens of millions of degrees. As the gas compresses, atoms lose their electrons, forming a plasma that emits high-energy X-rays. Some of this energy escapes as radiation, some falls into the black hole, and some is funneled into narrow jets that shoot outward at high speeds. Every detail of this process aligns with predictions made by general relativity and accretion physics. No other known object can reproduce these conditions. Even today, Cygnus X1 remains one of the most studied X-ray sources. In 2021, new measurements using the Very Long Baseline Array showed that Cygnus X1 is farther away than previously believed, about 7,200 light-years, implying that both the black hole and its companion star are more massive than earlier estimates. This refinement strengthened the conclusion that the source is indeed a black hole, not a neutron star. As instrumentation improves, so does the clarity of the picture. The story behind the discovery carries an emotional weight, rooted not in poetry, but in the persistence of measurement. Scientists spent years refining detectors, recalibrating instruments, and cross-checking data. The final conclusion did not come from a single observation, but from a long chain of evidence, each piece supporting the next. What began as a mysterious signal became the turning point for an entire field of astronomy. Black holes can be established through what falls inward. Matter accelerates, heats, and vanishes from view, leaving signals that can be measured and compared. But that picture does not remain complete. When quantum physics is brought into the same frame, the behavior of black holes no longer appears perfectly fixed or eternal. From that tension comes the idea that even these objects may change slowly over time, not by collapse or explosion, but through a gradual process tied to quantum effects themselves. Part 3. Why did Stephen Hawking claim that even black holes slowly evaporate into nothingness? The idea that the strongest objects in the universe slowly leak their own mass into space sounds impossible at first contact. Black holes were defined by one rule: nothing escapes. Not light, not matter, not information. Their gravity was supposed to be absolute. Yet in 1974, Stephen Hawking showed that this rule, as solid as it seemed, could not survive when quantum physics entered the picture. His calculation forced scientists to accept that even black holes slowly evaporate. A conclusion as unsettling as it is inevitable. To understand why Hawking reached this point, we have to trace the environment around a black hole with careful steps. Outside the event horizon, the boundary where escape becomes impossible. Space is not empty. Quantum field theory treats the vacuum as a restless background, full of fluctuations appearing and disappearing in fractions of a moment. These fluctuations are not random noise. They are a measurable part of how particles behave. Experiments in laboratories, including the Casimir effect and spontaneous emission from atoms, confirm that the vacuum is packed with activity, even when no real particles are present. John Wheeler once described the vacuum as a foam of fleeting possibilities. That description captures the right scale. Quantum fields near a black hole's horizon are constantly producing pairs of virtual particles. Under normal conditions, these pairs annihilate almost instantly. But near the horizon, gravity changes their fate. Hawking's key realization was simple in logic, but deep in consequence. When a pair forms near the event horizon, one particle can fall inward, while the other escapes outward. Once separated, they cannot recombine. The particle that escapes behaves like real radiation. The particle that falls inward carries negative energy relative to infinity. A mathematical statement, meaning the black hole must lose mass to satisfy conservation. In natural language, every escaped particle subtracts a tiny amount from the black hole's mass. This outward glow, predicted by Hawking, became known as Hawking radiation. It is incredibly faint for large black holes. A black hole with the mass of the Sun has a temperature measured in billionths of a Kelvin, far colder than the cosmic microwave background. It cannot radiate faster than the universe warms it, but small black holes, if they exist, would evaporate rapidly, producing bursts of high-energy particles. The formula behind this radiation, which Hawking derived using quantum field theory in curved spacetime, relates temperature to mass in a way that makes small black holes hot and large black holes cold. Although we do not show the equation here, the meaning is easy to state. The temperature is inversely proportional to mass. The idea was radical because it demanded that general relativity and quantum mechanics be applied simultaneously. General relativity describes gravity as the curvature of spacetime, a smooth surface without inherent grain. Quantum mechanics describes fields with fluctuations at every scale. Hawking placed a quantum field on curved spacetime and let the mathematics evolve. The result was not optional or adjustable. The radiation emerged directly from the rules. The theory left no room for exceptions. Black holes radiate, and if they radiate, they must eventually evaporate. The scientific community responded slowly but steadily. Early skepticism came from the unfamiliar combination of theories. Many physicists were uncomfortable with mixing quantum mechanics and relativity without a full quantum theory of gravity, but repeated analysis confirmed Hawking's result. In the decades that followed, the prediction became one of the cornerstones of modern theoretical physics, appearing in textbooks, lectures, and research on the early universe. Laboratory analogues, such as sonic black hole experiments, have detected phenomena consistent with Hawking-like radiation, offering indirect but meaningful support. And the implications reach far beyond mathematics. The universe is filled with black holes formed from collapsing stars, detected through X-ray systems, gravitational wave mergers, and galactic centers. NASA's Chandra Observatory, ESA's XMM Newton, the Event Horizon Telescope, LIGO, and Virgo have all confirmed the abundance of these compact objects. Every one of them will, over immense timescales, lose mass through Hawking radiation. Even Sagittarius A star, the supermassive black hole at the center of the Milky Way, weighing roughly 4 million suns, will eventually evaporate. But the timescale for that process is so large that ordinary numbers become meaningless, around 10 to the power of 67 years. For comparison, the universe is only about 1.4 times 10 to the power of 10 years old. This raises an interesting point. Black holes are often thought of as endpoints, the final product of collapse. Hawking's result transforms them into temporary objects. Their lifetimes are immense, but not infinite. A black hole does not freeze time forever. It simply slows its own decay so dramatically that the loss becomes invisible across human and even galactic timescales. The universe, however, is patient. Behind the discovery lies a story that reveals Hawking's persistence. He began exploring the thermodynamics of black holes in discussions with physicist Jacob Bekenstein. Bekenstein had suggested that black holes should have entropy, a measure of information content, and that this entropy should be proportional to the area of the event horizon. Many dismissed the idea, believing black holes were too simple to hold entropy. But Bekenstein's argument was grounded in physical reasoning. If black holes swallow matter, they must store the information in some form. Hawking initially disagreed with Bekenstein, but when he re-examined the mathematics, he found the entropy relationship emerging naturally from the equations. That observation pushed him to compute radiation, which then confirmed the idea that black holes have temperature and entropy like physical systems. Once these pieces aligned, a new picture formed. Black holes obey the same thermodynamic rules as any other system. The surface area of the horizon behaves like entropy. The temperature behaves like any object with thermal radiation. Energy loss through radiation reduces mass. General relativity, once thought to create perfect sinks, instead creates objects that evolve, cool, and eventually fade away. The radiation itself has not been observed directly for astrophysical black holes, but this is no weakness. The predicted temperature is far below the cosmic microwave background, making detection physically impossible with current technology. This absence does not challenge the theory. It simply acknowledges that the universe's background glow overwhelms the faint heat of massive black holes. For smaller hypothetical black holes, those formed in the early universe, Hawking radiation might be strong enough to detect. Experiments and observational programs continue to search for signatures, such as bursts of high-energy gamma rays or unusual cosmic ray events. The theoretical community has expanded Hawking's work into multiple directions. Some study black hole evaporation in the context of inflationary remnants. Some explore how quantum information behaves as the horizon shrinks. Others use semi-classical methods to model radiation for complex black hole geometries. Each of these efforts is built upon the original insight. Quantum fields behave differently near curved spacetime boundaries, and that behavior carries measurable consequences. Remarkably, the discovery of Hawking radiation also exposed one of the deepest puzzles in physics. The information paradox. If black holes evaporate completely, what happens to the information contained in the matter that fell in? Quantum mechanics demands that information be preserved. Hawking radiation, however, appears to carry no trace of the original structure. This contradiction is still unsolved. Research from string theory, loop quantum gravity, and holographic dualities continues to explore possible resolutions. But the paradox itself is evidence of how deeply Hawking's work reshaped the conversation. As the picture stands today, Hawking radiation is not an optional idea. It emerges directly from quantum theory, applied to gravitational backgrounds. It matches the thermodynamic behavior predicted for horizons. It is consistent with quantum field calculations performed by multiple independent researchers, and it sets a long-term fate for black holes that aligns with the universe's evolution as modeled by cosmology. Even without direct detection, it fits the framework with a coherence that few predictions achieve. So when Hawking asserted that black holes evaporate, he was not proposing a metaphor or speculation. He was describing the unavoidable intersection of quantum mechanics and gravity, a place where even the most massive objects obey rules written at the smallest scales. If black holes can change through quantum effects, then the explanation cannot remain confined to gravity alone. It points toward the behavior of light itself and the limits of how it can be described. In that region, where light refuses to behave in only one way, familiar categories begin to lose their reliability. What once appeared separate starts to overlap, and descriptions that worked in isolation no longer hold on their own. Part 4. Why does light switch between being a wave and a particle, as if it lives two lives at once? Light shattered physics the moment scientists tried to trap it inside a single definition, because every careful experiment insisted on telling two incompatible stories at the same time. At the end of the 19th century, light appeared to be the most well-understood phenomenon in all of science. James Clerk Maxwell's equations, completed in the 1860s, described light as a self-propagating electromagnetic wave, oscillating through space at a constant speed of about 299,792 kilometers per second. Those equations worked flawlessly. They predicted radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays as one continuous family. To many physicists, this felt like closure. Light was a wave. Full stop. Then experiments began to disagree. One of the earliest cracks appeared in the photoelectric effect. When light shines onto a metal surface, electrons can be ejected. Classical wave theory predicted that brighter light should always knock out more energetic electrons, regardless of color. But laboratory measurements showed something else entirely. Below a certain frequency, no electrons emerged at all, no matter how intense the light became. Above that threshold, electrons were released instantly, even under very weak illumination. The energy of those electrons depended only on the color of the light, not its brightness. In 1905, Albert Einstein explained this by proposing that light arrives in discrete packets of energy, later called photons. Each photon carries an amount of energy proportional to its frequency. If the energy is insufficient, no electron escapes. If it is enough, the electron is released immediately. This was not a metaphor. It was a quantitative explanation that matched experimental data exactly. For this work, Einstein later received the Nobel Prize in Physics in 1921. Yet accepting photons created a deeper problem. If light consists of particles, why does it produce interference patterns? When light passes through two narrow slits and strikes a distant screen, it forms a series of bright and dark bands. This pattern is characteristic of waves, overlapping and interfering with one another. Thomas Young demonstrated this behavior as early as 1801, long before quantum theory existed. What unsettled physicists in the 20th century was that the same pattern appeared even when light intensity was reduced so far that photons arrived one at a time. Each individual photon landed at a single point on the detector, like a tiny impact. But after many photons accumulated, the wave-like interference pattern gradually emerged. The behavior refused to simplify. Each photon behaved like a localized particle when detected, yet the distribution of many photons followed the mathematics of a wave. Physicists tried to force light back into a single category, but every attempt failed. If light was treated purely as a wave, the photoelectric effect became impossible to explain. If it was treated purely as a particle, interference patterns had no cause. The contradiction was not philosophical, it was experimental. Detectors, photographic plates, and later electronic sensors all recorded the same result. By the 1920s, the conclusion became unavoidable. Light does not choose between being a wave or a particle. It follows quantum rules that do not match classical intuition. Richard Feynman later summarized this unease bluntly. We choose to examine a phenomenon which is impossible, absolutely impossible, to explain in any classical way. That statement was not rhetorical. It reflected decades of precise measurements. To understand how quantum mechanics resolved the conflict, physicists changed the question. Instead of asking what light is, they asked what light does in different experimental setups. This shift mattered. When light travels freely through space, its behavior is described by a wave equation that predicts probabilities. The wave does not represent a physical ripple in a material medium, but a mathematical structure that assigns likelihoods to where detection events may occur. When light interacts with matter, when it strikes a detector, a photographic plate, or an atom, it exchanges energy in discrete amounts. That exchange appears particle-like. The wave description predicts where photons are likely to arrive. The particle description explains how energy is transferred when they do. This was not a compromise. It was a redefinition of what physical description means. The mathematics of quantum mechanics formalized this behavior through the concept of a wave function. For light, this wave function evolves smoothly in space and time, following equations closely related to Maxwell's classical waves. But the act of detection does not reveal the wave itself. It reveals a single outcome. Over many repetitions, the statistical pattern of outcomes matches the wave prediction exactly. Laboratory experiments reinforced this view repeatedly. In the 1970s and 1980s, single photon sources and ultra-sensitive detectors allowed physicists to study light at the most granular level possible. Each photon was detected as a localized event. No detector ever recorded half a photon or a smeared impact. Yet the overall distribution continued to follow interference laws with astonishing precision. Even more revealing were delayed choice experiments, inspired by John Wheeler. In these setups, the experimental configuration determining whether wave-like interference could appear was chosen after the photon had already passed the slits. The results showed no inconsistency. The photon did not decide earlier what it would be. The outcome depended only on the final measurement arrangement. Wheeler summarized the implication succinctly. No phenomenon is a phenomenon until it is an observed phenomenon. What made these experiments unsettling was not mystery for its own sake, but how reliably they worked. Every repetition, across laboratories worldwide, produced the same statistics. Modern technology depends directly on this behavior. Lasers rely on photons behaving as coherent waves while traveling, yet delivering energy as discrete packets when interacting with atoms. Solar cells convert individual photons into electrical current through photoelectric interactions. X-ray imaging depends on photons depositing quantized energy in detectors. The James Webb Space Telescope counts photons arriving from galaxies billions of light-years away, each detection event discrete, yet their collective pattern revealing wave-based diffraction and interference shaped by the telescope's optics. NASA's photon counting instruments do not debate whether light is a wave or a particle. They use both descriptions simultaneously, because reality demands it. What makes light especially instructive is that it forced physicists to abandon the idea that a physical object must have a single classical identity. Light is not half wave and half particle. It is fully quantum, obeying rules that produce wave-like statistics and particle-like interactions without contradiction. Physicists learned to stop asking which description is true, and instead ask which description applies to a given measurement. This approach spread beyond light. Electrons, neutrons, atoms, and even large molecules display the same dual behavior under controlled conditions. The rules discovered through light became universal. Feynman once remarked that the double-slit experiment contains the only mystery of quantum mechanics. He meant that understanding why the experiment works requires accepting quantum rules as fundamental, not reducible to classical pictures. Careful measurements have confirmed that the wavelength associated with light depends on its energy, following the relation discovered by Max Planck and Einstein. Higher energy photons correspond to shorter wavelengths. This relationship is measured daily in spectroscopy, astronomy, and materials science. It is not speculative. It is calibrated into instruments used by ESA, NASA, and observatories across the world. What began as a confusion about light reshaped the entire structure of modern physics. It taught scientists that probability is not a temporary placeholder for ignorance, but an intrinsic feature of how nature operates at small scales. Light does not carry a hidden classical identity waiting to be revealed. It carries a quantum state that produces different observable outcomes depending on how it is tested. This understanding did not emerge overnight. It came from decades of experiments, debates, failed interpretations, and refined measurements. What survived was not a story, but a framework that continues to predict experimental results with unmatched accuracy. Today, no physicist designing detectors for space telescopes, particle accelerators, or quantum communication systems doubts wave-particle duality. It is built into every calculation. It shapes how mirrors are polished, how sensors are cooled, and how data is interpreted. Light taught physics a difficult lesson. Nature does not organize itself around human intuition. It organizes itself around rules that only reveal their structure through careful observation and repeated measurement. If light cannot be confined to a single classical description, then the same logic must extend to the particles from which matter is built. At the scale of atoms, electrons no longer occupy one fixed condition at a time. Their behavior follows quantum rules that allow several possible states to coexist until an interaction forces one outcome to be recorded. Part 5. Why does superposition hint that particles exist in many states until the moment we look? Nothing in quantum physics unsettles the classical picture of nature more quickly than superposition. It is the idea that a particle can occupy several states at once. Several positions, several energies, even several paths. Until the instant someone performs a measurement. And once that measurement occurs, the spread of possibilities collapses into a single outcome. This behavior forces a question that pierces directly into the foundations of physics. If measurement selects a state, then what was the particle before anyone looked? To understand how scientists reached this idea, we have to go back to the early 20th century, when the structure of atoms began to reveal patterns classical physics could not reproduce. Spectral lines, the distinct colors emitted or absorbed by gases, showed that electrons inside atoms could only occupy specific energy levels. These levels were discrete, not continuous. Niels Bohr's model captured the pattern mathematically, but it did not explain how electrons jumped between levels without ever passing through intermediate energies. Something was missing, and the gap grew wider as measurements improved. In 1926, Erwin Schrödinger introduced a new description. Instead of treating particles as point-like objects, he treated them as wave-like solutions spread through space. The equation he developed predicted the spectral lines with remarkable accuracy. The electron inside hydrogen no longer orbited like a tiny planet. It formed a standing wave, a cloud of probability density around the nucleus. This probability cloud was the electron's superposition, a mathematically precise combination of all states it could occupy. The following year, the 1927 Solvay Conference brought together some of the sharpest scientific minds in history: Einstein, Bohr, Schrödinger, Heisenberg, Born, Dirac. Photographs from that Congress remain iconic. Physicists gathered in formal suits, standing on the edge of a new reality they were struggling to interpret. They debated fiercely. Heisenberg argued that the wave function, this mathematical spread of possibilities, was the most complete description possible. Max Born reasoned that the square of this wave function represented probability. Schrödinger objected, uncomfortable with the idea that particles did not possess definite properties until measured. Einstein refused to accept that nature relied on chance at its core. Yet, experiment after experiment supported the probabilistic picture. Superposition became unavoidable. One of the clearest examples came from atomic physics. Electrons bound to atoms can exist in several energy configurations at once. For instance, if an atom is prepared in a combination of two energy levels, separated by a precise frequency, the resulting state produces an oscillation that can be measured. These oscillations lie at the heart of atomic clock technology. The cesium-133 clock, the foundation of global timekeeping, relies on electrons switching between two hyperfine energy states. But before measurement, the electron does not wait in one state or the other. It exists as a quantum mixture, a superposition, until the moment a microwave pulse drives the transition or a detector measures the state. The operation of the clock depends on this dual state, the frequency of oscillation between these levels. Precisely 9,192,631,770 cycles per second defines the second in the International System of Units. Nothing in this definition would be possible without superposition. Timekeeping, satellite navigation, and global synchronization depend on the behavior of electrons existing in multiple energy states at once. Superposition, in this context, is not a theoretical curiosity. It is infrastructure. Lasers provide another example. A laser depends on stimulated emission, a process where excited atoms release identical photons when triggered. For the atoms to remain ready for stimulation, they must be placed in coherent superpositions. Inside a laser cavity, trillions of atoms share linked quantum states, forming a synchronized ensemble. This quantum coherence allows each photon to match the next with precise wavelength and direction. Without superposition, lasers would not produce their narrow beams or maintain stability across large distances. Superposition also shapes the behavior of electrons in solids. In a metal or semiconductor, electrons occupy quantum states extended across the entire material. These are not single locations, but combinations of all possible positions the electron can take. The entire structure of electronic bands, the foundation of transistors, LEDs, and modern computing, requires superpositions of atomic orbitals. Again, superposition is not decoration. It is a functional ingredient of technology. Despite its importance, the underlying meaning of superposition can be challenging to visualize. The most direct way to see it is through interference. Consider a particle traveling through two paths toward a detector. If we do not measure which path the particle takes, the wave-like components of the quantum state interfere. Bright and dark bands form, but if we place detectors to determine the path, the interference pattern disappears. The particle behaves like a classical object choosing a route. This change occurs because measurement collapses the superposition. Richard Feynman captured this difficulty accurately when he said, "We choose to examine a phenomenon that is impossible, absolutely impossible, to explain in classical terms." His words are not exaggeration. The two-path experiment has been performed with photons, electrons, neutrons, helium atoms, fullerene molecules containing 60 atoms, and even entire Bose-Einstein condensates. The interference pattern remains as long as the system is isolated from measurement, and it collapses when information about the path becomes available. This pattern, so consistent across different systems, confirms superposition as a universal feature of the quantum world. The story behind these discoveries also carries a quiet emotional weight, rooted not in philosophy but in the persistence of experimenters. Physicists spent years refining detectors sensitive enough to measure single photons. They cooled atoms to near absolute zero to uncover quantum behavior, unspoiled by thermal effects. They created vacuum chambers to isolate molecules from stray interactions. The transition from early electron diffraction in the 1920s to modern molecular interferometry took decades of instrument design and iterative improvement. Every improvement confirmed the same principle. Quantum states exist as combinations of possibilities until measured. Modern quantum technology continues to exploit this principle. Quantum computers use qubits, units of information that can occupy multiple states at once. A qubit in superposition can encode more information than a classical bit, and can explore multiple computational paths simultaneously. But to maintain this superposition, qubits must be isolated from environmental noise. Oxygen molecules, stray photons, and thermal vibrations can collapse the state prematurely. This fragility reflects the same challenge physicists encountered in early interference experiments. The environment becomes a measuring device unless carefully controlled. As John Preskill remarked, superposition is the engine of the quantum world. His statement is literal. It is the resource that drives quantum computation, quantum sensing, and quantum communication. Superposition enables entanglement, which in turn allows paired particles to share linked states across distance. In atomic clocks, it produces stable oscillations. In lasers, it produces coherence. In superconductors, it allows electrons to form collective states with zero electrical resistance. Everywhere we find advanced quantum technology, superposition sits at the center. Even in astronomy, superposition plays a role. The light, recorded by space telescopes such as JWST, Hubble, and ESA's Gaia, arrives as photons that have traveled for millions or billions of years. Each photon's quantum state evolves continuously through cosmic space. The interference patterns, observed in interferometry, used to measure stellar diameters, exoplanet atmospheres, and gravitational lensing, depend on maintaining the phase relationships between these photons. Superposition extends across cosmological distances, not just laboratory tables. Yet with all this evidence, the simplest question remains unanswered. What is a particle before measurement? Quantum mechanics does not answer this directly. It provides a predictive framework that tells us the probabilities of outcomes. It describes how the wave function evolves. It explains how these probabilities collapse under interaction. But the underlying nature remains outside the theory. This is not a deficiency, but a reflection of how quantum laws operate. The wave function encodes all allowed states. Measurement selects one. What exists prior to selection is the superposition itself. A complete and testable mathematical description. Physicists have proposed interpretations, from many worlds to hidden variables. But none change the experimental results. And across every experiment, the principle remains the same. A quantum system evolves as a combination of states until an interaction forces a definite outcome. That outcome becomes the measured reality. The mathematics is consistent. The data is consistent. The phenomena repeat across systems, scales, and environments. Superposition is not optional, it is structural. So when we say a particle exists in many states, we are not describing something mystical. We are describing a quantum state that allows multiple configurations simultaneously, each contributing to observable behavior. Measurement reduces that state. But until that moment, the quantum object behaves as the superposition requires. This is how atoms produce spectral lines, how electrons conduct in solids, how lasers operate, and how qubits perform calculations. Superposition is the operational reality of the microscopic world. If particles do not occupy a single fixed state, then the systems built from them cannot behave as perfectly steady clocks. At atomic scales, the passage of time is tracked through quantum transitions, and those transitions inherit the same rules of superposition and uncertainty. Part 6. Why is the time shown on your phone secretly controlled by quantum behavior inside atoms? The second ticking inside your phone is not a number on a screen. It is the echo of electrons jumping between two quantum states inside atoms thousands of kilometers away. Every minute you check, every navigation path you follow, every banking signal sent across continents depends on a microscopic transition so regular that it has become the backbone of global timekeeping. This extraordinary precision raises a striking question. Why does time itself depend on quantum behavior? To see how this happened, we have to return to the mid-20th century, when scientists realized that mechanical clocks, with pendulums, springs, and gears, would never achieve the stability demanded by modern science. No matter how well crafted, a pendulum's period drifted with humidity, temperature, and material imperfections. Even quartz clocks, though vastly more stable, still accumulated small errors. Astronomers needed better precision to track planetary motion. Physicists needed better precision to test relativity. Engineers planning satellite systems needed unbroken synchronization. This pressure pushed scientists toward atoms, objects that behave the same way everywhere in the universe. The first breakthrough came in the 1950s with cesium-133. Every cesium atom has electrons arranged in energy levels determined by quantum mechanics. Among these, two hyperfine levels, separated by a precise amount of energy, produce a natural oscillation when stimulated by microwaves. These oscillations occur at an exact frequency, 9,192,631,770 cycles per second. This number is not estimated. It is measured with astonishing repeatability. And because atoms do not wear down, stretch, or corrode, their oscillations remain stable across long periods. In 1967, the international scientific community defined the second using this transition in cesium-133. From that moment onward, timekeeping moved out of the domain of mechanical engineering and into the domain of quantum physics. Every second on Earth became tied to electrons switching between two allowed states. This is the foundation of the atomic clock. Inside these clocks, cesium atoms are cooled, isolated from magnetic fields, and exposed to microwaves. When the frequency matches the natural difference between the two hyperfine levels, the atoms absorb energy and switch states. An electronic feedback loop locks the microwave oscillator to this resonance, ensuring the clock never drifts. This behavior hinges on superposition. Electrons inside the atom do not simply move from one level to another. They form a quantum mixture of both levels, oscillating between them at the characteristic frequency. By monitoring this oscillation, scientists extract a clock signal far more stable than any macroscopic device. The accuracy is so extreme that a cesium clock would lose less than 1 second over millions of years. But as technology advanced, researchers found they could do even better. Strontium lattice clocks, developed at institutions like GILA and NIST, trap strontium atoms in a grid of laser light. Instead of using microwave transitions, they use optical transitions, occurring nearly 100,000 times faster. The faster the oscillation, the finer the measurement. These clocks now reach uncertainties on the order of 1 part in 10 to the power of 18. To put that into perspective, they could measure a difference in altitude of just a few centimeters, because gravity's influence on time becomes noticeable at that scale. This gravitational effect is not theoretical. Einstein predicted in 1915 that time would run slower in stronger gravitational fields. In simple terms, clocks tick differently at different heights. For decades, this prediction remained untested. But with the advent of atomic clocks, physicists could finally measure the phenomenon. In 2010, the team at NIST placed 2 aluminum ion clocks on shelves, separated by only 33 centimeters. The higher clock ticked faster, exactly as general relativity predicted. This was not a philosophical insight. It was a measurable change in the flow of time caused by a small difference in altitude. This gravitational sensitivity is why GPS requires quantum clocks. Satellites orbit Earth at altitudes around 20,000 kilometers. At this height, gravity is weaker, so time runs faster for the satellite clocks than for clocks on Earth. Without correction, GPS positions would drift by kilometers each day. To compensate, engineers incorporate relativity directly into the system. The clocks on satellites are adjusted to tick slightly slower, so once in orbit, they synchronize with Earth-based clocks. Every navigation direction you follow relies on this delicate balance between quantum oscillations and curved space-time. The story behind the development of atomic clocks demonstrates how physics shifted from large-scale machinery to the smallest components of nature. Early prototypes involved hardware challenges: magnetic shielding, vacuum chambers, microwave cavities. Scientists had to isolate atoms from the environment so quantum behavior could dominate. Any stray collision with air molecules or electromagnetic interference could disturb the oscillation. Decades of refinement produced clocks with unprecedented stability, each refinement revealing more ways in which time is tied to the quantum world. The path from cesium beam designs to optical lattice clocks was long, experimental, and filled with engineering detail. Modern optical clocks are so precise that they show time not as an abstract flow, but as a measurable property of physical systems. These clocks can detect the tiny variations caused by continental drift. They can track changes in Earth's gravitational field. They can probe whether fundamental constants change over long periods. One proposal from physicists at JILA suggests using optical clocks to detect dark matter, because certain models predict that dark matter interacting with Earth could cause measurable shifts in the oscillation frequency. This idea shows how deeply quantum timekeeping has penetrated modern research. In astronomy, these clocks play a growing role. Networks of precise time standards allow radio telescopes to combine signals across continents in techniques such as very long baseline interferometry. This method contributed to the Event Horizon Telescope images of black hole shadows. The timing precision needed for these observations depends on stable quantum transitions. Even the pulsar timing arrays, searching for low-frequency gravitational waves, rely on stable clocks to calibrate signals spread across thousands of kilometers. In this way, atomic timekeeping supports the exploration of the universe on the largest scales. The environment inside an atomic clock is delicate. To achieve their stability, atoms must be shielded from thermal noise. Strontium lattice clocks cool atoms to microkelvin temperatures, near absolute zero. Cesium beam clocks use ovens to produce atomic beams, then magnetic selectors to filter states. Every part of the setup reflects decades of refinement. Each time the instruments improve, time itself becomes more sharply defined. This precision opens doors for new science. Quantum clocks also reveal a subtle truth about time. It is not universal. Two clocks at different altitudes tick at different rates. Two clocks experiencing different speeds tick differently. Even temperature shifts and magnetic fluctuations can influence the delicate quantum states. What we call a second is not an inherent property of the universe. It is a carefully maintained standard built on the behavior of electrons. Timekeeping depends on controlling and understanding that behavior. American physicist David Wineland summarized this with a line that has become central to the field. The atoms themselves are the pendulums of the future. His words were literal. Atoms, not gears, define the motion of time. Quantum transitions, not mechanical cycles, govern the clocks that coordinate communication, science, and navigation. Everything from financial transactions to spaceflight depends on the smooth oscillation between two quantum states. This marks one of the clearest examples of how quantum physics shapes everyday life. As atomic clocks continue to advance, researchers are pushing toward nuclear clocks, devices that use transitions inside atomic nuclei instead of electrons. These transitions are even more stable and less sensitive to environmental disturbances. If successful, nuclear clocks could improve precision by another order of magnitude. Such clocks could allow scientists to test general relativity at smaller scales, search for new forces, and measure variations in fundamental constants. These goals highlight how quantum timekeeping remains an active frontier. Time is not simply measured, it is investigated. If atoms can maintain extraordinary regularity, then light interacting with them cannot remain arbitrary or uncontrolled. Under quantum rules, light itself can be shaped into a state of remarkable order, where frequency, phase, and direction behave with a precision unlike anything found in natural sources. Part 7. Why did quantum physics create the laser, the most perfect beam of light humanity has ever made? Ordinary light scatters, flickers, and spills in every direction. Yet a laser slices through space with precision so sharp that even distant mirrors perched on the moon can reflect it back to Earth. The beam is too clean, too focused, too disciplined to emerge from any classical description of light. Only quantum physics contains the rule that allows this transformation, the rule that turns chaotic photons into a perfectly synchronized stream. That rule is stimulated emission, a phenomenon predicted long before technology was ready to use it. To understand why a laser is so different from a light bulb, we must look inside atoms themselves. Atoms contain electrons arranged in quantized energy levels. These levels are fixed by quantum mechanics. No electron may drift freely between them. When an electron drops from a higher level to a lower one, it emits a photon, the smallest unit of light. This process is spontaneous emission, and it produces photons with random phases and directions. This is the light we see from lamps, stars, candles, and nearly every natural source. It is bright, but uncoordinated. In 1917, Albert Einstein proposed something new. While studying the interaction between light and matter, he predicted that an incoming photon could trigger an excited atom to emit an identical photon. The emitted photon would match the trigger exactly. Same frequency, same direction, same phase. Einstein named this process stimulated emission. This prediction emerged from quantum reasoning, not classical wave theory. There was no analog in the classical world. At the time, Einstein saw little immediate use for it. Technology simply could not amplify the effect, but the idea remained in physics, waiting. Decades later, experimentalists began testing his prediction. Microwave masers, the predecessors of lasers, were built in the 1950s by Charles Townes and colleagues. These devices used ammonia molecules to produce coherent microwaves through stimulated emission. The coherence was striking. The emitted waves stacked neatly, reinforcing each other, unlike any other source known at the time. Townes later reflected on the moment with the simple line, "It was a tool waiting for the world to discover what it could do." His remark described not only an invention but a change in the direction of science. The leap from masers to lasers required moving from microwaves to visible light, a far more demanding task. Visible light oscillates nearly 100,000 times faster. To produce it coherently, scientists needed materials where electrons could be placed in carefully controlled excited states. Ruby crystals, helium-neon gas mixtures, and later semiconductor structures provided that environment. When the first ruby laser was built in 1960, it emitted a pulse of deep red light. Narrow, clean, and unlike anything produced before. Photographs from the era show researchers standing beside glowing rods and mirrored cavities, aware that they were witnessing a technology both powerful and precise. The age of lasers had begun. Inside a laser cavity, everything depends on controlled quantum behavior. A population of atoms or molecules is pumped into an excited state. Mirror-lined cavities confine photons so that each emitted photon triggers more emission. The photons bounce back and forth, building an avalanche of identical copies. The key is that every photon produced carries the same properties. They move in lockstep, creating a beam that stays tight over great distances. This cooperation does not arise naturally. It requires quantum structure. The sharpness of a laser beam is not poetic exaggeration. It is measurable. NASA has used lasers to measure the distance between Earth and the Moon since the Apollo missions. Retroreflectors left on the lunar surface return a small fraction of the beam. The round-trip measurement, about 768,000 kilometers, is precise to within a few millimeters. Only laser coherence allows such accuracy. A light bulb diffuses instantly, but a laser retains its shape across astronomical scales. The universe allows the beam to stretch, but not scatter. Modern research uses lasers for even more extreme precision, interferometers in gravitational wave observatories, such as LIGO and Virgo, use laser beams to measure changes in distance smaller than 1/10,000th of the diameter of a proton. These changes arise when spacetime itself stretches during the passage of gravitational waves. This measurement depends entirely on quantum light. If the laser beam flickered even slightly, the instrument would lose sensitivity. The fact that LIGO detected gravitational waves in 2015 confirms not only Einstein's prediction, but the stability of modern laser systems. The ability to hear black holes collide depends on photons synchronized by quantum rules. Lasers also reveal themselves across the microscopic world. Electron traps, cooled near absolute zero, use laser beams to remove thermal motion from particles. JWST uses laser-calibrated gyroscopes to maintain its orientation in space. Atomic clocks use lasers to trap strontium atoms in optical lattices, grids of light that hold atoms nearly motionless. Each of these applications depends on coherence, stability, and the ability of photons to carry identical properties through space. These features do not emerge from classical randomness, they emerge from quantum structure. The story behind laser development also carries a quieter thread. The persistence of small, incremental improvements. Materials researchers tested thousands of compounds to find ones with reliable transitions. Engineers built cavities with tighter alignments, mirrors with smoother surfaces, and power supplies with lower noise. Quantum physicists designed methods to cool atoms, isolate optical transitions, and control spontaneous decay. Each refinement widened the technological landscape. The final precision we see today came from decades of adjustment. Lasers also raised new opportunities in measurement. Spectroscopy transformed when laser light became available. Scientists could probe the energy structure of atoms and molecules with unprecedented clarity. When the hydrogen 1 second, 2 seconds transition was measured with laser techniques, its precision reached 1 part in a quadrillion. Accuracy beyond anything imaginable prior to the laser era. Such measurements test quantum electrodynamics, the most precise theory in physics. They also provide benchmarks used by NASA and ESA when calibrating instruments for deep space missions. In this way, light controlled by quantum rules feeds back into the study of the universe. Even the devices used to encode and transmit information today rely on this structure. Fiber optic cables carry laser pulses across continents. The stability of those pulses determines how much information can be packed into each signal. Every video call, every data center, every streaming platform depends on lasers acting as carriers of quantum coherent information. This shift is not philosophical. It is the foundation of global communication. Without lasers, the speed of the modern world collapses. Yet at the center of all this lies a single requirement. An atom must be ready to respond when a photon arrives. Stimulated emission only happens when atoms sit in the right quantum state. Achieving this condition requires energy pumping, careful temperature control, and isolation from noise. A laser works not because matter is naturally cooperative, but because scientists force atoms into conditions where quantum rules can express themselves clearly. This reveals a deeper point. The perfection of a laser is not accidental. It is engineered quantum behavior. And each photon in the beam carries the signature of that engineering. The science is clear, and so is the impact. From surgery to manufacturing, from astronomy to computing, from navigation to spectroscopy, lasers maintain their remarkable property. Every photon behaves as though it knows exactly what the others are doing. This discipline is not taught. It is a product of quantum mechanics, a direct consequence of electrons occupying precise energy levels, responding to photons with exact timing, and emitting copies without variation. No classical system can reproduce this cooperative behavior. When physicists describe a laser beam as coherent, they are describing a level of order achievable only when quantum transitions are synchronized. This synchronization is the heart of the device. It is why a laser can cut metal, track spacecraft, measure space-time curvature, read information from storage devices, and cool atoms to temperatures only a fraction above absolute zero. Every one of these applications rests on photon consistency, produced by stimulated emission. The beam is not just bright. It is stable in a deeply controlled way. As we examine the layers of this technology, one conclusion emerges with gentle clarity. The laser is the most precise expression of quantum mechanics the world interacts with daily. Its cleanliness, its narrowness, its stability, all originate from the microscopic rules governing how electrons respond to light. And those rules, once viewed as abstract, now form one of the most versatile tools in science and engineering. The path from Einstein's 1917 prediction to 21st century instruments demonstrates how quantum insights reshape entire fields. When light is shaped into an instrument of extreme precision, its role extends beyond illumination and measurement. At that level of sensitivity, even the medium light travels through can no longer be treated as perfectly still. Subtle variations in space-time itself begin to leave measurable traces. Part 8. Why can LIGO detect ripples in space-time smaller than 1/10,000th of a proton? Space itself betrayed its silence the moment two black holes collided more than 1 billion light-years away, because that distant violence nudged Earth by an amount so small it should never have been measurable at all. For most of scientific history, space was treated as an empty stage. Objects moved through it, forces acted within it, but space itself remained passive, rigid, and silent. Even after Albert Einstein published general relativity in 1915, describing gravity not as a force but as the curvature of spacetime, many physicists still believed that this geometry would remain forever beyond direct observation. The equations allowed for ripples, gravitational waves. But those ripples seemed impossibly weak. By the time they reached Earth, they would stretch and squeeze space by less than the width of an atomic nucleus. No instrument, it was thought, could ever detect them. Einstein himself doubted they would be observed. Yet, the equations did not lie. Whenever massive objects accelerate asymmetrically, especially when compact objects like neutron stars or black holes orbit each other, energy must be carried away. In general relativity, that energy travels outward as waves in spacetime itself, not waves through space, but waves of space. Distances expand and contract as the wave passes, changing the separation between objects without pushing them through space. This is not metaphor. It is geometry in motion. For decades, gravitational waves remained a prediction without evidence. Indirect confirmation arrived in the 1970s through the Hulse-Taylor binary pulsar, whose orbital decay matched exactly the energy loss predicted by gravitational radiation. That discovery earned a Nobel Prize in 1993, but it still left one challenge unanswered. Could spacetime waves ever be detected directly? The difficulty was scale. A strong gravitational wave passing through Earth changes lengths by a fraction of about 1 part in 10 to the 21. For an object 1 kilometer long, that amounts to a change smaller than the diameter of a proton. For a 4-kilometer instrument, the change is still less than 1/10,000th of a proton's width. Any ordinary vibration, thermal motion, seismic noise, passing trucks, even distant ocean waves, would overwhelm such a signal instantly. Detecting gravitational waves required measuring distance more precisely than any experiment in history. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, was designed to do exactly that. Built in the United States, with 2 identical facilities separated by nearly 3,000 kilometers, LIGO consists of perpendicular vacuum arms, each 4 kilometers long. At their intersection sits a beam splitter. A laser beam is divided into 2 identical beams, sent down the arms, reflected by ultra-polished mirrors, and recombined. Under normal conditions, the beams return in perfect synchrony, cancelling each other out at the detector. But if a gravitational wave passes through, it stretches one arm while compressing the other, altering the relative travel times of the beams. That tiny mismatch produces a detectable interference pattern. The concept is simple. The execution is not. LIGO's lasers must remain extraordinarily stable. The mirrors, known as test masses, are suspended by multiple layers of vibration isolation to shield them from seismic motion. The vacuum inside the arms is among the largest and cleanest ever created, reducing air molecules that could disturb the beam. Every component is engineered to eliminate noise at levels far below anything experienced in everyday life. Quantum physics plays a central role here. Laser light itself is governed by quantum fluctuations, shot noise, the random arrival times of photons. Limits measurement precision. Thermal vibrations at the atomic level introduce additional uncertainty. To overcome these limits, LIGO employs techniques such as power recycling, signal recycling, and quantum squeezing, reducing uncertainty in the measurement direction most relevant for gravitational waves. This is not optional sophistication. Without quantum-level control, the signal would remain buried forever. On September 14, 2015, both LIGO detectors recorded a nearly identical signal, separated by 7 milliseconds. The time it takes light to travel between the sites. The waveform matched precisely the prediction for two black holes, with masses about 30 times that of the Sun, spiraling together and merging. In less than a second, they released energy equivalent to several solar masses converted entirely into gravitational radiation. At its peak, the power emitted exceeded that of all stars in the observable universe combined. Yet when the wave reached Earth, it shifted the 4-kilometer arms by less than 1/10,000th the diameter of a proton. Kip Thorne, one of the architects of LIGO, later described the moment with quiet precision. The universe telling us its story through gravity's voice. That voice was faint, but unmistakable. Subsequent detections followed. Binary black hole mergers, neutron-star collisions. In 2017, LIGO and its European partner Virgo observed gravitational waves from a neutron-star merger, accompanied by electromagnetic signals across the spectrum. Telescopes worldwide watched the same event unfold in light. For the first time, astronomy listened and looked at the same cosmic catastrophe simultaneously. This marked the birth of gravitational wave astronomy. What makes these measurements extraordinary is not only their sensitivity, but their reliability. Each detection is matched against detailed numerical simulations of Einstein's equations. The waveform's frequency, amplitude, and decay encode information about the masses, spins, and distances of the sources. These are not guesses. They are extracted from the data through models tested across decades of research. NASA and ESA now integrate gravitational wave observations with space-based missions, studying black hole populations, stellar evolution, and cosmic expansion. Future observatories, such as the Space-Based Laser Interferometer Space Antenna, or LISA, will extend this listening range to lower frequencies, opening a window onto supermassive black hole mergers and early universe processes. LIGO's achievement rests on an insight that would have seemed impossible a century ago. Space-time itself can act as a messenger. Instead of detecting particles or light, the instrument detects geometry changing shape. No material object vibrates. No force pushes the mirrors. The distance between them changes because space changes. The detection also confirmed a deeper idea embedded in general relativity. That space-time is dynamic, not fixed. It can ripple, stretch, compress, and carry energy. Those ripples travel at the speed of light, preserving causal order. Nothing moves faster than light. Information propagates through geometry itself. The precision required to observe this forced physicists to confront the quantum nature of measurement. LIGO operates near the limits set by quantum uncertainty. Increasing laser power reduces photon noise but increases radiation pressure fluctuations. Lowering one source of noise amplifies another. Engineers balance these effects carefully, operating at the edge where classical engineering meets quantum physics. This marriage of relativity and quantum control is not theoretical. It is operational. The mirrors inside LIGO are among the most perfect objects ever manufactured, polished to atomic smoothness. Their suspensions behave like nearly ideal pendulums. The lasers remain phase-stable across kilometers. The entire system listens for changes smaller than any object it measures. And it works. What once seemed like a mathematical curiosity has become a new sense. Humanity now hears the universe through gravity, not metaphorically, but instrumentally. Every detection adds detail to a picture that light alone cannot provide. Black holes emit no light. Gravitational waves are the only direct evidence of their collisions. Neutron stars reveal the behavior of matter at densities beyond any laboratory. Space-time itself becomes the medium of information. The quiet lesson of LIGO is not drama, but humility. Nature does not scale its signals to human convenience. It operates at levels of subtlety that demand patience, precision, and trust in theory tested by measurement. The universe whispered. We learned how to listen. If space-time itself can carry information, then geometry is no longer a passive backdrop. Under quantum rules, connections can form between distant systems in ways that do not rely on any signal traveling through space. Behavior becomes linked, even when no exchange can be traced in between. Part 9. Why does entanglement allow two particles to behave like one object even when they're worlds apart? Two particles can be separated by kilometers, by continents, even by the distance between Earth and the Moon. And yet, the moment one is measured, the other responds in perfect coordination, as if distance itself had quietly lost its authority. For physicists raised on the idea that nothing travels faster than light, this behavior felt not just surprising, but deeply unsettling. Correlations appeared instantly, without any signal crossing the space between the particles. No energy moved between them. No information was sent in the ordinary sense. And yet the outcomes were linked with mathematical precision. This phenomenon came to be known as quantum entanglement. The story begins in the 1930s, when Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper questioning whether quantum mechanics could be considered complete. They described a thought experiment, now known as the EPR paradox, in which two particles interact and then separate. According to quantum theory, their properties remain correlated even when far apart. Einstein famously disliked this implication, calling it spooky action at a distance. His concern was not poetic, it was technical. If quantum mechanics allowed such correlations, did it violate relativity's speed limit? For decades, the question remained unresolved, largely because it was impossible to test experimentally. Entanglement was treated as a mathematical curiosity, useful for calculations, but detached from measurable reality. That changed in the 1970s. In laboratories equipped with increasingly precise photon sources and detectors, physicists began to create pairs of entangled particles and measure their properties independently. The most decisive tests came from experiments inspired by John Bell, who derived inequalities that any local, classical theory must satisfy. Quantum mechanics predicted violations of these inequalities. If experiments confirmed those violations, local hidden variable explanations would be ruled out. In 1982, Alain Aspect and his team in France performed a landmark experiment using entangled photons. Their measurements violated Bell's inequalities, exactly as quantum mechanics predicted. No classical explanation survived. Subsequent experiments refined the setup, closing loopholes related to detection, efficiency, and timing. By the early 21st century, entanglement had been demonstrated repeatedly, under increasingly strict conditions, across distances of kilometers. The result was unambiguous. Entangled particles behave as a single quantum system, even when spatially separated. Importantly, this does not allow faster-than-light communication. Each individual measurement outcome is random. Only when results from both sides are compared do the correlations emerge. Relativity remains intact. No signal travels between the particles at the moment of measurement. Instead, the quantum state describing the pair is non-local from the start. This distinction matters. Entanglement does not involve particles sending messages to each other. It involves a shared description that cannot be decomposed into independent parts. To make this accessible, physicists often use analogies. One common example involves paired coins. Imagine two coins prepared so that whenever one lands heads, the other always lands tails, no matter how far apart they are tossed. Before looking, neither coin has a definite outcome. The correlation exists without a predetermined result. This analogy is imperfect, but it captures one key feature. The system must be described as a whole, not as two separate objects. Quantum experiments show this behavior with extraordinary consistency. Entangled photons exhibit correlated polarizations. Entangled electrons show linked spin orientations. Even large collections of atoms, atomic ensembles cooled near absolute zero, can be entangled, behaving as a single quantum state distributed across space. NASA and ESA rely on entanglement-aware models when interpreting data from precision instruments. Atomic clocks, for example, can use entangled states to reduce noise and improve timing accuracy. Experiments have demonstrated that entanglement enhances measurement sensitivity beyond what independent particles could achieve. Gravitational wave observatories like LIGO also benefit indirectly. Quantum squeezing techniques, which rely on entangled photon states, reduce measurement uncertainty in laser interferometry. Without these methods, detecting space-time distortions smaller than 1/10,000th of a proton would be impossible. Entanglement has moved from philosophical debate to engineering tool. One of the most striking confirmations came from space-based experiments. In recent years, satellites have distributed entangled photons over distances exceeding 1,000 kilometers. Detectors on Earth measured correlations that matched quantum predictions precisely. Distance did not weaken the entanglement, only interaction with the environment. Decoherence could disrupt it. This highlights a crucial point. Entanglement is fragile, not mystical. Thermal noise, stray electromagnetic fields, and material imperfections all destroy quantum correlations quickly. Maintaining entanglement requires extreme isolation and careful control. Its persistence is not guaranteed. It must be protected. This fragility is why entanglement is so revealing. If it were an illusion or artifact, it would collapse under experimental scrutiny. Instead, it survives exactly as long as quantum theory predicts. And no longer. John Wheeler captured this tension in a remark often quoted for its clarity. Behind it all is surely an idea so simple, so beautiful, that we will all say to each other, how could it have been otherwise? What Wheeler emphasized was not mystery for mystery's sake, but inevitability. Once quantum states exist, entanglement follows mathematically. It is not an added feature. It is built into the structure of the theory. Modern quantum communication systems exploit this directly. Quantum cryptography uses entangled photons to distribute encryption keys. Any attempt to intercept the particles disturbs the entanglement, revealing the intrusion immediately. This is not speculative. Operational quantum key distribution networks exist today, tested under real-world conditions. Quantum computing relies even more heavily on entanglement. Qubits gain their power not merely from superposition, but from entangled relationships that allow the system to explore correlations across many states simultaneously. Without entanglement, quantum algorithms lose their advantage. This is not an interpretation. It is a requirement, confirmed by both theory and experiment. What makes entanglement conceptually challenging is that it forces a revision of how physical systems are defined. In classical physics, objects have their own independent states. In quantum physics, the state of a system may belong only to the whole, not to its parts. This does not mean particles lose individuality in a mystical sense. It means that the most complete description available cannot be factored into independent components without losing information. Decades of experimental data support this view. Bell tests, loophole-free experiments, satellite-based entanglement distribution, and precision metrology all converge on the same conclusion. Entanglement is not optional. It is unavoidable. Importantly, physicists have learned to describe entanglement without invoking faster-than-light influences. The correlations emerge from the structure of the quantum state established when the particles interact. Measurement does not transmit influence. It reveals relationships already encoded. This is why entanglement respects causality. No usable signal travels instantaneously. Information still requires classical communication channels to be compared and interpreted. Relativity remains unviolated. What changes is not speed, but separability. From a practical standpoint, this insight has reshaped experimental design across physics. Instruments are built with quantum correlations in mind. Noise models incorporate entanglement effects. Data analysis assumes non-local correlations when warranted. Even cosmology has begun to explore whether early universe quantum correlations left imprints on large-scale structure. While these ideas remain under investigation, they demonstrate how deeply entanglement has penetrated scientific thinking. Entanglement does not replace classical physics. It extends it, precisely where classical assumptions fail. It is tempting to treat entanglement as a puzzle to be solved away, but decades of work suggest otherwise. It is not a glitch. It is the architecture. If information can be shared across space without moving through it, then the limits that constrain ordinary machines no longer apply in the same way. Devices designed around quantum connections do not process possibilities one by one. They operate within a structure where many outcomes coexist and influence the result together. Part 10. Why might quantum computers solve problems no classical machine could handle in the lifetime of the universe? A machine that explores more possibilities at once than there are atoms in the observable universe is not a metaphor, not a slogan, and not a promise for the distant future. It is a direct mathematical consequence of how quantum states combine. For more than 70 years, classical computers have shaped how humanity understands computation. At their core lies a simple idea. Information is encoded in bits, each of which must be either a 0 or a 1. Whether those bits are represented by vacuum tubes, transistors, or microscopic circuits etched onto silicon, the rule never changes. At any given moment, each bit occupies one definite state. All computation unfolds as sequences of operations acting on those fixed values. This framework has been astonishingly successful. Classical computers have mapped genomes, simulated climate systems, guided spacecraft, and connected billions of people. Yet even as their power grew, physicists began to recognize an unavoidable boundary. Some problems scale too quickly. As the size of the system increases, the number of possible configurations grows exponentially, and classical machines are forced to examine them one by one. Even with the fastest supercomputers on Earth, many such problems remain hopelessly out of reach. Quantum computing emerges not as an upgrade to classical logic, but as a different way of representing information itself. The fundamental unit of quantum computation is the qubit. Unlike a classical bit, a qubit is not restricted to a single value at a time. It can exist in a superposition of 0 and 1 simultaneously. This is not uncertainty or approximation. It is a precisely defined quantum state that can be manipulated, interfered with, and measured according to the rules of quantum mechanics. When multiple qubits are combined, the consequences become dramatic. 2 classical bits represent one of 4 possible states at any moment. 2 qubits, by contrast, can exist in a superposition of all 4 states at once. With each additional qubit, the size of the state space doubles. 10 qubits span 1,024 possible states. 50 qubits span more than 1 quadrillion states. A few hundred qubits span a number of configurations that exceeds the estimated number of atoms in the observable universe. This growth is not a claim about speed. It is a statement about representation. Quantum computers do not test possibilities one after another. They encode an entire landscape of possibilities into a single evolving quantum state. John Preskill of Caltech summarized this shift with characteristic clarity. Quantum computing lets nature compute with its own rules. Those rules include superposition, entanglement, and interference. Superposition allows many possibilities to coexist. Entanglement links qubits into unified states that cannot be decomposed into independent parts. Interference amplifies correct computational paths while cancelling incorrect ones. Together, these effects allow certain problems to be approached in fundamentally new ways. Building such machines, however, is extraordinarily difficult. Most leading quantum computers today use superconducting circuits as qubits. These circuits are fabricated from materials that lose all electrical resistance when cooled near absolute zero, typically below 20 millikelvin. At these temperatures, quantum effects that would normally be drowned out by thermal noise become accessible and controllable. Microwave pulses manipulate the quantum states of the circuits, performing logical operations with exquisite timing precision. Other approaches exist as well. Trapped ions use electromagnetic fields to confine individual atoms in vacuum. Photonic systems encode qubits in the polarization or phase of light. Each platform has advantages and challenges, but all face the same fundamental obstacle. Quantum states are fragile. Any unwanted interaction with the environment, heat, electromagnetic noise, material defects, causes decoherence. When decoherence occurs, the delicate superposition and entanglement that give quantum computers their power degrade into classical mixtures. the computation loses its quantum advantage. This is why quantum error correction is essential. Unlike classical error correction, which can copy bits freely, quantum error correction must protect information without directly measuring it. Researchers encode logical qubits across many physical qubits, using carefully designed correlations to detect and correct errors indirectly. This requires additional qubits, increasing the size and complexity of the system. Progress has been steady, not sudden. Experiments have demonstrated error-corrected logical qubits, with lifetimes exceeding those of individual physical qubits. These results confirm that scalable quantum computation is not forbidden by physics. It is constrained by engineering. Despite these challenges, quantum computers have already demonstrated capabilities beyond classical reach in specific tasks. In 2019, a superconducting quantum processor performed a random circuit sampling task faster than any known classical algorithm could simulate. While the practical usefulness of that specific task was limited, the result demonstrated that quantum hardware had crossed a threshold into regimes inaccessible to classical machines. The real promise lies elsewhere. One of the most compelling applications is quantum simulation. Many systems in chemistry and materials science are quantum mechanical at their core. Electrons in molecules occupy entangled states that classical computers struggle to represent efficiently. Quantum computers can model these systems directly, using qubits to represent quantum degrees of freedom without exponential overhead. This capability could transform drug discovery, catalyst design, and materials engineering. Simulating the electronic structure of complex molecules with chemical accuracy remains beyond classical reach for all but the smallest systems. Quantum algorithms offer a path forward, grounded in the same physics that governs the molecules themselves. Optimization problems represent another frontier. Power grids, transportation networks, and logistics systems often involve searching vast configuration spaces for optimal solutions. Classical algorithms rely on heuristics and approximations. Quantum approaches, such as quantum annealing and variational algorithms, explore whether quantum interference can guide searches more efficiently through these landscapes. It is important to be precise here. Quantum computers will not outperform classical machines at every task. Many problems remain better suited to classical architectures. Quantum advantage is problem-specific, not universal. This distinction is central to responsible understanding. Quantum computers are not replacements for classical computers. They are complementary tools. Classical machines excel at arithmetic, data storage, and control. Quantum machines excel at representing and manipulating certain complex quantum structures. In practice, future computing systems will likely integrate both, with classical processors orchestrating tasks and quantum processors handling specialized subroutines. NASA and ESA already explore quantum algorithms for trajectory optimization, sensing, and data analysis. These efforts remain experimental, but they reflect a broader recognition. Quantum information processing is becoming a practical scientific instrument, not merely a theoretical curiosity. What makes this moment remarkable is not the speed of progress, but its inevitability. Once information is treated as a physical quantity governed by quantum laws, quantum computation follows naturally. It is not an invention imposed on nature. It is a technology that aligns computation with the structure of reality itself. That alignment comes with limits. Decoherence, noise, and resource overhead ensure that quantum computers will always require careful control and modest expectations. Exaggerated claims fade quickly under experimental scrutiny. What remains is a steady, evidence-driven expansion of capability. Each year, qubit coherence improves, gate fidelities rise, error-corrected demonstrations grow more robust. None of these milestones alone changes the world. Together, they mark a transition from possibility to infrastructure. At its core, quantum computing is not about doing everything faster. It is about doing certain things differently. By allowing nature's own correlations to carry computational meaning, what began with quantum uncertainty now finds a practical form. Waves and particles, superposition, entanglement, even ripples in space-time, are no longer only concepts to describe. They operate together inside devices, built, tested, and refined by human hands. At this point, one fact stands on its own. The universe has always followed quantum rules. What has changed is not nature, but our ability to design systems precise enough to work within those rules. Thank you for spending this time here. If listening through these ideas brought even a small moment of clarity or interest, I truly appreciate your presence. A like or a subscribe is a simple way to support the work behind these long-form explorations. And wherever you are listening from, I hope the rest of your night unfolds at an easy, steady pace.